Now we are going to see about the Unit 5, channel coding and speed spectrum. Here we have Huffman coding, Shannon-Fenner coding, error control coding of linear block codes, Hamming codes, convolutional codes, Viterbi decoder algorithm, and introduction to speed spectrum, pseudo noise sequence, direct sequence speed spectrum with frequency hopping speed spectrum. So first we'll see about source coding theorem. So here it has to satisfy two functional requirements. The code words produced by the encoder should be in the binary form. The source code is uniquely decodable. So we have the discrete memoryless source sent to encoder. The bits is being given in the binary sequence. The discrete memoryless source of entropy h of s, the average code word length of any source encoder is bounded to the L bar should be greater than h of s, where h represents the fundamental limit on the average number of bits per signal. L minimum should be equal to h of s, where the efficiency is given by eta is equal to h of s by the average length. We have lossless coding and lossy coding. In the lossless coding, exact reconstruction of the original data from the compressed data is possible. In the lossy coding, some information of the original signal is being getting lost at the time of compression. For an efficient source encoder, we are going to calculate the average number of bits code efficiency. First, we are going to see about the Huffman coding. This is the procedure for Huffman coding. The source symbols are listed in the order of decreasing probability in stage 1, denoted as the leaf node. Combine the last two source symbols probabilities and obtain a new source symbol probability. The probability of the new signal is placed in the next stage in accordance with its value. The procedure is repeated until to have two source symbols in the stage. Assign bit 0 and bit 1 from the root node to the leaf node. Let us consider this example where the probability is given as S0 is 0.4, S1 is 0.2, S2 is 0.2, S3 is 0.1, S4 is 0.1. First, we are going to list the probability in the decreasing order. For the last two code words, we are going to assign 0 and 1. When we add 0.1 and 0.1, it goes to 0.2. We are going to mention here 0.2. For the last two code words, we are going to mention it as 0 and 1. We are going to add, we are going to get 0.4. 0.4 is being written at the top. This 0.4 bringing it down, this 0.2 bringing it down. When we add these two last probabilities, which we have assigned 0 and 1, it comes to 0.6. We are going to consider it as first code word. The last two, we are going to denote it as 0 and 1, and the stage ends here. Now we are going to determine the code word for each probability in the reverse order. Next, we are going to list the number of bits. First, we are going to calculate the average length. It is given by n bar is given by summation k is equal to 0 to L minus 1 pk into nk. So for the first one, we have the probability 0.4, number of bits 2. For 0.2, number of bits 2, 0.2, number of bits 2, 0.1, number of bits 3, 0.1, number of bits 3. So it has been calculated to 2.2 bits per symbol. Next, we are going to calculate the entropy h, that is summation k is equal to 1 to m pk log base 2 1 by pk. For all the 5 probabilities, we are going to calculate. It comes to around 2.121 bits per second. Next, we are going to calculate the efficiency, eta is equal to entropy by average length. It comes nearly to 96.4%. Next, we are going to calculate the redundancy. Mu is 1 minus eta. The value comes around 0.036 in percentage. It comes around 3.6%. So this is the Huffman coding. Thank you.